Hello, everybody. Today I will be talking about topics 18.1 and 18.2, which are about static electricity, conductors, and insulators. So let's start off with static electricity. This is something that you experience in your everyday life. Sometimes if you're walking across the floor and then you touch a doorknob, you might get a shock. That is from static electricity. So we've known about static electricity as humans for a long time. Back around like 500 BC, the Greeks noticed that when they were polishing amber, so that's what this is right here, it would attract small pieces of straw. So imagine this is straw instead of a feather, but same idea. The word electric is actually derived from the Greek word for amber, which is electron. And in this picture here, you see a little guy with his hand on a Van der Graaf generator, which is a common physics demonstration. It generates static electricity, and his hair is spreading around because he's got an excess of charge building up and causing his hairs to repel each other. So, kind of the basics of electric charge. There's two types of electric charge, positive and negative. And these are just properties of matter. Okay. And we see that like charges repel each other. So here, if you have two negative balloons, they'll repel each other, but opposite charges will attract. So if you have positive charges on the wall here and negative charges on the balloon, they will attract each other. And that force decreases with distance. So if I increase the distance, the force between those two objects, either like or opposite, will decrease. So our basic pieces of matter that contain charge are protons and electrons. So protons are our positive charges and electrons are the negative charges. Remember back from chemistry, our positive charges, the protons are in the nucleus along with neutrons, and electrons orbit around the nucleus. This 1.6 times 10 to the negative 19, that is the charge of a proton or an electron. And this C right here, that unit is a coulomb. And that is how we essentially quantify charge. That's our unit for charge. The charge on a proton is positive 1.6 times 10 to the negative 19 coulombs, and on an electron is negative 1.6 times 10 to the negative 19 coulombs. Q is the variable you'll see for charge, and sub E means proton or electron. It'll just be a positive or a negative 1.6 times 10 to the negative 19. That 1.6 times 10 to the negative 19 coulombs is a fundamental charge, meaning that smaller charges don't exist in isolation in nature for any significant amount of time. So the smallest charge that we'll encounter in everyday life is 1.6 times 10 to the negative 19, or some integer value of that. There are smaller charges that exist, though. They exist inside protons and neutrons. Electrons are their own special fundamental particle. They don't really break down. But a proton and a neutron actually are. They're made up of these things called quarks that have fractional charges. So this here, the positive 2/3, we have two up quarks and then one negative 1/3 charge. That would be a proton. And a neutron has no charge, so the positive 2/3 and the negative 1/3 have to balance out. So we can have fractional charges, they just don't exist on their own. We have to break down a proton or a neutron to see that, and that just doesn't happen in nature. But still super cool. All right, so the law of conservation of charge states that charge cannot be created or destroyed. So, kind of like energy and momentum, this is another law of conservation. So, we'll never see charge just popping out of nowhere. It has to be transferred or, shared from one object to another. In extreme environments, though, so like a particle accelerator or some sort of fusion reaction inside of a star, we can have particles being created or particles being destroyed. And that's described by that famous equation E equals mc squared. So let's say we're in one of those extreme environments and we have some change of mass. Okay? And that would be described by energy over c squared, where c is the speed of light. Let's say we create an electron. So we have energy being converted into mass. That is, by this formula, allowed. What has to happen, though, is we have to create another particle that has the same charge but opposite sign in order to have the conservation of charge. So when an electron is created, what's also created is this thing called a positron. And it has the same mass and same charge as the electron. But it's this funky thing. It's actually an antimatter particle. And anyways, they're super funky, but it does allow for the law of conservation of charge to, still be valid. And when a positron and an electron, let's say we're going the other direction, they just ran into each other. So we have a positron, we have an electron. If they run into each other, they actually annihilate. I think that's how I spell that. I'm not really sure. But they annihilate each other. There's some release of energy because we have some change in mass there. But overall, there is a net conservation of charge. So here we have a positive and a negative charge, which have a net together, no charge. They balance each other out. When they annihilate, that charge has still stayed at zero. So, right. Conductors and insulators. So, kind of basic stuff there. Conductors are materials that have loosely bound electrons or free electrons, like salt water and metals. It allows the electrons to move easier. An insulator is something like rubber or glass with tightly bound electrons. Talk about how we can exchange charge, so charging an object. One way is by contact. So if you rub two materials together, imagine rubbing a balloon on a shirt, or bringing a charged object in contact with another can cause a separation of charge or cause an object to be charged. So, for example, this person whose hands are on this Van der Graaf generator that has a net positive charge, since they're touching that, this person will end up with a net positive charge as well. And that's what causes her hair to repel each other because her hair is all positively charged. Another way that you can charge something is by induction. That's bringing a charged object in close proximity with another object, neutral or charged. We can induce charge. So let's look over here at this picture. So here we have two neutral objects, and then we bring this positively charged rod close to these two objects. We don't even have to touch them. What will happen is that the negative charges will be attracted to the positive charges, leaving the other side of these two spheres that are in contact right now, leaving that positive. If we then separate these two objects and then remove that charged rod, what happens is now this object on the left has a net negative charge and the object on the right has a net positive charge. So we have charged these two objects by induction. We never even touched the objects with this charged rod. The other photo over here is showing, here the top two pictures are insulators. So we're not having a huge movement of positive or negative charges from one side to the other. But when you bring a charged object in close proximity, what happens is you get a polarization of the atoms. So when I bring that positive charge, the negative charges line up because they're attracted to that positive rod, and the opposite if that rod was negative. This last picture, though, is a conductor that has more freely moving electrons. So if you bring a negatively charged rod, those negative charges will be repelled to the other side of the whole object rather than just within the atoms. So not really many examples to go through with this topic, but here's an example from the book. Can you explain the attraction of water to the charged rod in the figure below? So this is a faucet, and water is coming out, and then it's being deflected. It's being pulled towards this charged rod. So we're not told what the charge is on this rod, but it doesn't actually matter. So as the water is coming out of the faucet, it's bending over this way. So let's say that this rod over here is negatively charged. Water is a polar molecule, meaning that there's a natural separation of charges in the H2O molecule. And in those little water molecules, so if I don't know, I can't really draw this, but anyways, the positive charges will be, I'll just draw this like this, positive, oh gosh. So here's my molecule here. The positive charges and negative charges will be separated, where up above they were more kind of just random. They weren't all lined up in one direction or not. But then once they encountered this charged object, all of those water molecules lined up in a certain orientation, causing a net attraction of the stream of water. Sorry for kind of bumbling there at the end, but hopefully that was helpful, and thanks a lot.